In 3.3, we're going to combine a lot of what we have learned about calculus, a lot that we learned in pre-calculus, all together to really focus on how to accurately sketch the curve of a function using things like extrema, points of inflection, concavity, all of those things sort of tying together. So we're going to start each of these problems by analyzing things the way we did in pre-calc. We're going to talk about domain restrictions. Are there vertical asymptotes? Are there holes in the graphs? We can obviously find x and y intercepts. Sometimes that's going to involve using a graphing calculator or Desmos. We can think about even back to Algebra 2 when we talked about end behavior as x goes to infinity or negative infinity, what's happening to the function, as well as horizontal asymptotes. So that's really refreshing all of those pre-calc skills. But now we can add to the tools that we have. We can add to the things that we knew how to do in pre-calc and some in Algebra 2 by identifying our critical numbers so that we can determine behavior, where the function is increasing or decreasing, where we have relative extrema, where that derivative is changing signs, changing from positive to negative for a relative max or from negative to positive for a relative min. And then we can use our second derivative to give us information about concavity and where that concavity is changing. So we can identify points of inflection, which are where the second derivative is 0 and doesn't exist. We can identify that if the second derivative is positive, that means our function f is concave up. If it's negative, that means our function f is concave down. And if needed, we can use the second derivative test to determine our relative extrema. We can also determine those using a f prime number line. So thinking through these tools that we have, we can start exactly the way that we just talked about, thinking through the pre-calculus things. Are there domain restrictions? Are there vertical asymptotes or holes? What is the end behavior of this function going to look like? Then we can analyze the first derivative, our critical numbers, to figure out where the function is increasing or decreasing, where we have relative extrema. Then we can analyze the second derivative to figure out where our points of inflection are and where our graph is concave up or concave down. And we can put those things together to graph and sketch out the function. And that really is the point of what we're doing here. And notice that we're saying sketching. We're going to have the general shape, but this is not necessarily a precision type of graphing that we are doing right now. So for this first example here, we are given the function, the first derivative, and the second derivative. So we don't actually have to do any of the computations there. Looking at this function, I can tell that this original function is going to be undefined when x is equal to 1 because there's a vertical asymptote there. There aren't any holes and there are no other domain restrictions. I can also tell, since the degree of the numerator is less than the degree of the denominator, that we're going to have a horizontal asymptote at y equals 0. So I'm going to go ahead and write all that information down, and then I'm also going to go ahead and add those asymptotes to my graph. Now, if I didn't normally have my first derivative, which I do, I would now take the derivative and then I'm going to analyze that derivative, making a sign chart. So I notice that f prime is undefined when x equals 1, but that makes sense. So is the original function. So I'm only going to be looking for values that make the derivative 0. And that's only going to occur when the numerator is 0, which means my only critical number is going to be 1/3. So analyzing, and I'm also going to just add that I do have that asymptote here. I do want to know what's happening with my derivative around that asymptote. So if I plug in something like 0, I'm going to get a negative number. If I plug in something between 1/3 and 1, like 1/2, I'm going to get a positive number. If I plug in something greater than 1, like 2, I'm going to get a negative number. So I'm plugging those into my derivative equation and seeing what happens. So what does this tell me? This tells me that I have, and I'm not going to try and squeeze it over here in this little box on the left, but that I have a relative min at x equals 1/3. And let's actually figure out what that is as an ordered pair. So if I have 1/3 for x and I plug that into my original function, I think I'm going to get negative 9/4, so I can go ahead and plot that point as well. I can also tell from this f prime chart that we are decreasing from negative infinity to 1/3 and from 1 to infinity, and that this function is increasing from 1/3 to 1. And that's going to help me when I'm sketching the graph. That's going to help me identify what should be happening with the slope of my original function, because that is the first derivative, the slope of that function. Now I'm going to go ahead and check out what's going on with the concavity and analyze the second derivative. It is also undefined when x is 1, but again, that's just going to be represented using a dotted line. And the only way that this derivative is going to be 0 is if x is 0. So let's analyze. If I plug in, notice that the bottom of this second derivative is always going to be positive, so I really only have to pay attention to what happens up top. If I plug in a negative number, I'm going to get 6 times a negative number, that's going to be negative. If I plug in a positive number, whether it's between 0 and 1 or more, I'm going to get a positive number. So now I know that my graph is concave down from negative infinity to 0 and concave up from 0 to 1, and then it stops, and from 1 up to infinity. I can also tell from this that I do have a point of inflection, or an inflection point, at 0. If I plug 0 into the original function, I'm going to get -2 over 1. So 0, -2 is going to be a point of inflection. Our point of inflection happens to be our y-intercept, so let's find our x-intercept. What would make the numerator 0 in the original function? That would be, oops, let's write this correctly. That would be 2 over 3. And then just for safe measure, because I want to know the shape, right now I don't have any ordered pairs on the right-hand side of this function, so I'm just going to plug in a couple numbers so I actually have legitimate points on my graph on the right. If I plug in 2, I'm going to get 4. If I plug in 3, I'm going to get 7 over 4. So I'm going to go ahead and add those points to my graph. And lastly, I need to think about the concavity while I am connecting the dots. So there's obviously 2 pieces happening to this function. So on the left-hand piece, it should be concave down all the way until we get to 0. And then it should turn around and become concave up as it goes up past or next to our asymptote. Obviously, this would look better on actual paper. On the right-hand side, I'm going to connect those 2 points that I do have, and that entire interval is concave up. So again, we're really just going through this checklist, identifying the things that we know from pre-calc, adding in what we know about the first derivative and the second derivative to really just get a pretty quality sketch of what's happening for this graph. Let's go ahead and look at a few more examples. So for number 1 here, we have a polynomial. It is a 4th degree polynomial. We don't have any domain restrictions, asymptotes, or holes. We should know from Algebra 2 that the end behavior is that both ends of this function to the 4th power are pointing upward. So as x approaches both positive and negative infinity, our function is approaching infinity, or the ends of the graph should look like they're going out. Now I want to find the derivative so that I can analyze it. So this is just a polynomial. I can just use the power rule to take the derivative. You can go ahead and use your graphing calculator or Desmos to find where that derivative is equal to 0 and put those on a number line. Those are our critical values, critical numbers. So using a graphing calculator or using Desmos, you're going to get that f prime exists everywhere, but it's 0 when x is -1.326. 0.469 and 1.607. And then if you check the signs there, you're going to get negative, positive, negative, positive. Which is telling me a few things. It's telling me where this function is increasing and decreasing. It's decreasing from negative infinity to negative 1.326 and from 0.469 to 1.607. I also have some relative extrema happening, since the derivative is going from negative to positive, both at negative 1.326 and at 1.607. So I'm going to have relative minimums there, and I'm going to have a relative max when x is 0.469. So I'm going to go ahead and add that information in. So I'm going to go ahead and add some of that information to the graph. So I'm going to remind myself that I know the end behavior, which I'll probably erase that later, but is going out on both ends. I'm going to plot my relative extrema. And then I'm going to start analyzing the second derivative. So our second derivative is going to be 12x squared minus 6x minus 8. So we can use a calculator again to find those critical values or those possible points of inflection. We're going to get negative 0.604 and 1.104. So I'm going to go ahead and set up my f double prime number line. So I can plug values into that second derivative to fill in this number line. I'm going to get negative, positive, negative, positive, which means I have 2 points of inflection happening when x is equal to negative 0.604 and 1.104. And I can just plug those into a calculator to find out what the actual value of the function is at each of those values. That also means I can determine where this function is concave up, which is going to be from negative infinity to negative 0.604 and from 1.104 to infinity, and where it's concave down, which is from negative 0.604 to 1.104. So I'm going to go ahead and identify all of that information, and I'm going to graph that point of inflection. So even right now with those inflection points plotted and our relative extrema plotted, we have a general shape. It's going to look sort of like a funky W, which makes sense since the leading coefficient is x to the fourth, or the leading term is x to the fourth. But let's just see if we can identify some intercepts here that are going to make our lives a little easier. 0, 0 is obviously an intercept. You could factor and simplify this to find that the other intercepts are 1, 0, and both plus and minus 2, 0. So let's go ahead and identify those and then plot them. So to find those, you obviously could factor an x out of everything, and you could use a whole bunch of different pre-calc and algebra 2 strategies to find the rest of those zeros during that time. Now I'm going to do my best to connect the dots and make sure I have that end behavior shape right and that the concavity is changing at my blue points and everything is going through each of those little individual dots that I have made. So again, that shape is going to look sort of like a W. So let's go ahead and look at the next example. I would recommend that you pause the video for this next example, that you get as far as you can get. And I did have the second derivative identified there for you just so you're doing a little bit less of the calculus work so that you can focus on graphing this function. So no domain restrictions, no holes or vertical asymptotes on number 2. End behavior is going to be similar to the last function. We're going to have both as x approaches positive and negative infinity. The function is approaching infinity. So now we need to find the derivative, find the critical values, and analyze them on a number line. So there's our first derivative, 4x over 3 times the quantity x squared minus 4 to the power of 1/3. That's going to be undefined when x is plus or minus 2. And it's going to be 0 when x is 0. So that gives us our critical values are going to be 0 and plus or minus 2. We can put those on our number line to analyze the behavior of our function. So the behavior of our function is decreasing from negative infinity to negative 2, and from 0 to 2, it's increasing from negative 2 to 0 and 2 to infinity. We can also see that we have a relative min at negative 2 and positive 2, and we have a relative max at 0. So we can go ahead and plug those values into our original function to find our relative extrema and then plot those on our graph. So now we have identified and graphed everything we need from our first derivative. We can go ahead and look at our second derivative, which is given to us. We can identify that the denominator will be 0 when x is plus or minus 2. Those were already critical numbers in f. The numerator will be 0 when x is plus or minus the square root of 12. So I'm going to go ahead and identify those as possible inflection points and make my number line for my second derivative. So I can see from my second derivative that this function is concave up from negative infinity to negative root 12 and from root 12 to infinity. And it's concave down everywhere else from in between negative root 12 to positive root 12. I can also tell that I have inflection points when x is equal to negative plus or minus root 12. So I'm going to go ahead and plug those values into my original function to find those inflection points and identify my concavity intervals. Lastly, we're going to identify our intercepts. We already know about plus or minus 2, 0. And if we plug in 0, we get negative 4 to the power of 2/3. So we have all of those graphed. So now, to the best of our ability, paying close attention to the concavity, we are going to connect those dots. Not perfect on an iPad, but probably not perfect on paper either. All right, we're going to do one more problem start to finish. I really encourage you to pause this video, try and graph the whole thing on your own, and then we're going to actually analyze a graph of a derivative and kind of tie this back to 3.2 on our last example. So looking at this problem from a pre-calc lens, no domain restrictions, no vertical asymptotes, no holes. There is a horizontal asymptote at y equals 0 since the degree of the numerator is less than the degree of the denominator. That's going to tell me a little bit about the end behavior of the graph is going to be approaching that asymptote both from negative infinity and positive infinity. Next, I'm going to find my derivative, find the critical numbers, and make an f prime number line. So our critical numbers are going to be plus or minus 1. We can make our sign chart. This function is decreasing from negative infinity to negative 1 and from 1 to infinity. It's increasing from negative 1 to positive 1. We can also tell that we have extrema happening both at negative 1 and positive 1. So decreasing to increasing means we have a relative min when x is negative 1 and a relative max when x is positive 1. So we can go ahead and plug those values into our original function to determine our extrema. And then we can go ahead and add those points to our graph. And then we can begin analyzing the second derivative. So looking at the derivative that we already have, it exists everywhere, or the second derivative, I'm sorry. It's going to be 0 when x is 0 or plus or minus root 3. So I'm going to go ahead and set up my second derivative number line and analyze the behavior. From that number line, I can see my concavity intervals. I can see my inflection points, the x values of my inflection points, and I'm going to go ahead and state that information on the left with the rest of this information and add those inflection points to the graph. After doing that, we've identified the only intercept that there is as well. So now it's a matter of connecting those dots. And actually, one of my inflection points is plotted incorrectly. Two of my points are plotted incorrectly. So I'm going to go ahead and fix those and connect the dots. That's what I get for not paying attention to the sign. There we go. Now those points look right. So I'm going to go ahead and connect the dots. When I'm doing that, I'm paying attention to the concavity, which is switching at my blue dots, and that the end behavior is approaching y equals 0 on both ends. And there we go. All right, last question, number 4. Given the graph of f prime of x and that f of x is differentiable everywhere, where f of x equals 0 when x is negative 2, 0, and 1, sketch the graph of f of x. So this information over here is just giving us our x-intercepts. So why don't we go ahead and graph those, negative 2, 0, 0, 0, and 1, 0. Now, we can use our derivative to identify anything else that we possibly could need. So since we have the graph of the derivative, we can use that for our critical values. So here's my f prime chart. My critical values are going to be at negative 1.215 and 0.549. So I can add those to my number line. I can look at the graph to see that this is positive, or it's above the x-axis, less than negative 1.215 and more than 0.549, and it's negative or below the axes in between those two critical values. The last thing I can do to help sketch this graph is I can look at my second derivative, which is going to give me some information about concavity. Remember, when we're thinking about our second derivative, we're analyzing the slope of our first derivative. Well, the slope is 0, what looks like, negative 1/3, based on that ordered pair. And it's decreasing to the left and increasing to the right. So I can tell that I'm going to have an inflection point when x is 1/3. I can also tell that I'm going to have some relative extrema at negative, when x is negative 1.215 and 0.549. Now, since we don't actually have the function, we can't plug in negative 1/3 or either of those critical numbers from f prime to actually find those values, which is why this is a sketch. What we can do is we can make sure that our graph is concave down from negative infinity to negative 1/3. At negative 1/3, it should start changing concavity. We can also make sure that somewhere around those two critical values, we have relative extrema happening. So this graph is going to be a very rough sketch because we don't even have the original function that we are graphing. So I am kind of putting points in there, but again, those points could be vertically shifted based on the fact that we don't know our actual function. So I'm going to try and connect the dots here as best as I can to make sure that I'm meeting all of the requirements that I know to be true. And there we have it. So one question that should be coming to your mind is, how much of this work do I need to show? How much do I need to have? No, you don't need to list everything out in this exact way. Domain restrictions, vertical asymptotes. This is sort of a checklist for you. If the problem simply says graph, you need to have as much of this information as needed to create a logical sketch of the graph that you're doing. If a question specifically asks you for some of this information, you should make sure that you're including that. But we'll talk more about this in class. Hopefully you got a great view of how to tie some previous knowledge to the calculus we have been learning in order to sketch functions. Thanks for listening.